And so what we're doing here is called problem solving using integration techniques. And the takeaway here is, think back to calculus, if we have a function, f of x, then f dash of x describes the rate of change of that function. So a couple of examples, often we talk about like the height of a tree, that was a common problem that popped up, the height of a tree, then h dash of t describes the rate at which the tree grows, the rate at which the height changes. And we also represent that as dh, delta h, the change in h with regards to the change in time. Similarly, we looked at volume questions, so the volume of water in a tank. V dash of t describes the rate at which the volume changes, and we can also notate that as dv on dt. So here we have some quantity, right? We have some height, some quantity, we have some volume, all right? And so we know if we differentiate it, we get a rate. Therefore, if we integrate a rate function, we get a quantity. Okay, that's what's going to pop up today. So we have here in our first example, a whole meal sandwich is eaten and converted to energy at a rate of 250 times 1 on t kilojoules per minute, t minutes after the sandwich is consumed. The function is valid over the interval from 1 to 181. So part A says, find the value of the integral from 1 to 121 of the function with regards to t. Okay, evaluate this integral. So we're going to do it manually, and then what we'll do is we'll convert it to 3 significant figures. So the integral of 1 on t is ln of t. So we have 250 ln of t from 1 to 121. So we have 250 ln of 121. Take 250 ln of 1. Now, this is popping up a fair bit. ln of 1 is 0, okay? So you put that in your calculator, ln of 1, that term's going to go to 0, so that whole term's 0. So this is our answer, 250 ln, 121. It doesn't really mean much until we convert it to a few figures for us, so that we can see what quantity is it talking about. So 250 ln 121, and I've got 1198, okay, 0.9. I'll talk again about 3 significant figures when we have large numbers, okay? The same things apply, like it does go on, but if we're rounding this, I'm going to write all the digits, okay? There's 4 digits, and I'm going to round the 4th one, okay? 8 rounds up, which means 9 rounds up, and so this to 3 significant figures would be 1200. Now, let's think about it. dE on dt, this is the rate at which energy is converted with regards to time. dE on dt. So we saw if we have the rate of change of height and we integrate it, then we get the height. If we have the rate of change of the volume, then we get the volume. If we have the rate of change of the energy, which we integrate, then we get the quantity of energy. So we had kilojoules per minute, and so our unit here is going to be kilojoules, okay? 1200 kilojoules in that sandwich, that whole meal sandwich. Delicious. Okay. Any questions about that?
It says, in like the sentence above, the function is valid at time
1 to 100. Oh, I did 121. Sorry. Yep. So let's change that to an 8. Same. That's the only thing. Sorry, I misread that. So what do we get when we type that in? 250 ln of 181. 1299, 1300. Okay. All right, thanks for that. Any others? Okay, part B. Let's find the energy function then. Find the energy function with regards to time. So if this is the rate of change of the energy function, then the energy function, okay, is going to be the integral of this. Just like if this is the height, then the integral of dh on dt is going to give us the height function. The integral of dv on dt is going to give us the volume function. So the integral of dE on dt is going to give us the energy function. So we've seen if we integrate this, we have 250 times 1 on t, but this time the difference is it's an indefinite integral. We don't have constraints. So we know it goes to 250 ln t, but because it's a indefinite integral, because it doesn't have those boundaries, we go plus c. See? All right. Now we're going to use the information provided in part B to find the function exactly. We want to know what is this c value. And so we're told, so that's e of t, we're told e of e squared, okay, when you substitute the number e squared into the e function, you get 550. So let's do that. Okay, all I've done is put e squared where the t value is. We're substituting e squared for t. So this will, ln of e squared is just 2. So we have 250 multiplied by 2. And so we can solve for c. C is 50. And so therefore the function is 250 ln t plus 50. Okay, so this can describe for you the energy received for any value of time. dE on dt describes the rate at which energy changes. Okay, now flicking over, we'll go through exam question 1 together. There's 2 exam questions in this booklet. Together today, we'll just do the first one. We may do the second one on Tuesday. So, let's have a read. We have a 12-hour music festival. It's going to be cranking. It starts at 12 noon, finishes at 12 midnight. And the rate dE on dt, we're not talking about energy this time. The rate at which patrons entered the venue is modelled by the function below. So dE on dt is the rate of entry. And so we have the function here. This is called a surge function, by the way. 220 te to the minus 0.4 t plus 15. It's valid from 0 to 12. Okay, the music festival goes for 12 hours, where t is the number of hours after 12 noon. All right, so that means when t equals 1 hour after 12 noon would be 1 p.m. And d and dt is the number of patrons entering the venue per hour. Before 12 noon, there are no patrons inside the venue, so there's no one starting in there. The graph is shown below. Okay, part A. Find the rate at which patrons entered the venue at 12 noon. Now, when we're confronted with a question like this, I think the first thing we should do is graph the function, because we're going to be using that graph to g-solve a number of features over the next few parts. Okay, you can see that from scanning ahead. So if we can pull out and draw a graph of it, I'm going to bring it up on, I've got the calculator thing now, so I'll bring that up too. And I would encourage everyone, if you've got your calculator, please pull it out, because we will go through a few integral calculus skills here as well to make sure we're all up to date. So graph the function there, 220 t e to the minus 0.4 t. We're in PRC 6.
3956.
Oh, fantastic. 3956.
220.
Share screen. And just maximize this. So in graph mode, 220 x. Okay, read it carefully. There's a t before the e. All right, and that has tripped people up in the past. 220 t e to the power of minus 0.4. And then we have a plus 15. Now, 2 things. We're given the graph, all right? It sketches the graph for us, which means those are the constraints we should use on the V window. Even if we're not given a graph, we are given a value for x to constrain. We're told it's valid from 0 to 12. So we should start looking at those things. So I'm going to graph it, and I'm going to change my V window just to match exactly the graph that they've given us. So for x, we're going from 0 to 12, and for y, we're going from 0 to 220. Let's graph that. Beautiful. Okay, let's get start answering some of the questions here. So, part A, find the rate at which patrons entered the venue. So this function here describes the rate. We want to know, well, what is the rate when time is 0 at 12 noon? That's the y-intercept. So we can just g-solve the y-intercept, and we can also evaluate that just by thinking about the function. So the function is 220 t e to the minus 0.4 t plus 15. Okay, if I put the number 0 when time is 0 into this equation, yeah, that part is going to be 1, but then we have this 0 here, 0 times 1. That whole part's 0, and so we're just left with 15. We g-solve the y-intercept, we get 15. So the answer to part A is when t equals 0, the dE on dt, the rate at which people are coming in, is 15. Let's put a unit. Okay, so let's examine the question. What unit can we specify? We're talking about patrons entering the music festival per hour. Okay, so that's told to us in the third sentence after the function, where t is the number of hours after 12 noon, and dE on dt is the number of patrons entering the venue per hour. So patrons per hour. All right, so right at the start of the music festival, there's about 15 people coming in per hour. Okay, use your calculator to find the time when the rate at which patrons entered the venue was at a maximum. So this is as simple as, this function describes when they're coming in, the rate at which they're coming in. When is this function maximized? So we're just going to go g-solve max. Okay. Now, we're asked when use time when the rate at which patrons enter the venue is at a maximum. And so when, well, it's when time is 2.5. Okay, let's answer that in the context of the problem. 2.5 hours after 12 noon. Remember, when time is 0, that corresponds with 12 noon. So that's 2:30 p.m. post midday. Okay. The model here implies that patrons continuously entered the venue. Identify the characteristic of the model that reflects this. How do we know patrons continuously entered the venue? So if we think about this graph, this is the rate at which patrons entered the venue. It's completely above the x-axis, okay? So here, sorry, it's at 15. Initially, they're coming in at 15. Up here, they're coming in at, what was our max? At time is 2.5, 217. Okay, it's always positive. It's always above the x-axis. Because it's always above the x-axis, people are always coming in. Okay, so that's what we'll say for part C. dE on dt is this is the mathematical way to write it. dE of dt is positive for 0 is less than t is less than 12. Okay, we're just saying the function is positive. And if you were to just articulate those words, if you write those words, the function is above the x-axis, the function is positive for the values of time that we're concerned with, full marks, okay? But that's one way we can communicate it mathematically. Okay, D, we've got two parts for D. On the graph of the function, provide a representation of the number of patrons that the model implies entered the venue between 1 p.m. and 4 p.m. So, what this is going to be, I'm going to demonstrate it for you first and then describe why. We're going to shade the region between 1 p.m. and 4 p.m. So out here. We're going to shade that region. Okay, that's how we're going to answer this part. So on the graph that you're presented with, we're going to shade that region. So, provide a representation of the number of So we've said this is a rate of change function. And what are we asked? We're asked a quantity. We're asked how many people came in. So if we want a quantity, well, that's going to be the integral. And what is integral? But area under the curve between 1 and 4. Okay? Area under the curve, the integral from 1 to 4 of the function. That's going to tell you how many people came in between time is 1 and time is 4. All right. So that's D part 1. We've shaded it. D part 2, it says calculator. So, because we've graphed the function, this is where we can just rely on the graph. We're going to go G-solve. We press the across arrow and we've got the integral button. And we've got a number of options here, but we're just doing a basic integral calculation that corresponds with F1. We want to know the area under the curve from x is 1 to x is 4. Okay. And we've got 613.5. Which is 614. Okay, 614 watt. What's our unit? So the rate is patrons per hour. Patrons per hour. So therefore the quantity is patrons. Between 1 and 4 p.m. we have 614 people enter the music festival. Okay, so can I just really draw out where have we drawn that from? Again, I'll take you back to this example, like V of t, and dV on dt. If this is the rate of change, then the integral of this gives you the quantity. This is the rate of change, so the integral of dE on dt gives us the quantity. What does the integral correspond with? Area under the curve, and we're interested in that time constraint between 1 and 4. So that's D part 2, 1 and 2 complete. Okay, everyone happy so far? All right, the rate dL on dt at which patrons left the venue over the 12 hours is modelled by this function. So they're introducing a new function for us, dL on dt. On the axis of page 2, sketch the graph of dL on dt. So, well, let's do that. Let's sketch both functions. And I'm going to describe to you as a SACE marker, exam marker, how we mark graphs. So we're going to graph both functions on the same axes. So that's 50x e to the minus 0.15x. And that's it. Okay, so for a feature like this, it can depend on the complexity of the function, but for sketching a feature like this, you sort of get 2 marks, really. 2 marks, 1 mark, depending on the complexity of the function. And so that means, depending how many marks a graph is for, can tell you how much detail is required. Here, 2 marks, 1 is for the shape, and 1 is for the approximate correct point of intersection. Okay, so I don't want you to just go, oh, okay, yep, looks like this. Okay, no, we need to know roughly where that is. Now, the way we give out marks for getting that in the right position, let's G-solve it and say, what is that point of intersection? Okay, we've got 6.44. So if that's my axis, let's say here is 5 and here is 6. Okay, now there's a box. All right, what's going to happen, let me have a look at your grid and I'll see what it corresponds with. So between 5 and 6. Okay. Between 5 and 6 and 122. Sorry, between 6 and 7 and 122 spares. Okay, so I've drawn a box there. all right, between 6 and 7, and between 120 and 140. Provided your point of intersection occurs within that box, you'll get the mark. Okay, so there's wiggle room, all right, where, you know, we err on the side of generosity, but that doesn't mean you just sort of go, oh yeah, it's about there. And it's amazing with graphs, guys. I really, really want you to get all the marks, okay? You have to get all the marks for graphs because you're literally just copying it from your calculator, all right? So we have the correct shape. We can see it some maximum here. Now, because of just, if we're just going like that, we're not getting the trend that it's actually going down a bit here as well. So there's one mark for having the correct shape. So that's demonstrating its concavity and its convexity, and another mark for getting that point of intersection correct. Make sure you get the marks for graphing. They're giveaway marks. Okay, any questions about how we allocate marks for graphs? All right, so we've sketched the graph, part E done. That's a generous 2 marks. Okay, find the time to the nearest half hour when the rate at which patrons enter the venue is the same as the rate at which patrons leave the venue. Okay, we just evaluated that before. We've already G-solved it up here. Okay, so they are equal when time is 6.44. Okay, it says find the time to the nearest half hour. Okay, so the nearest half hour is going to be 6.5. If you get half hours, well, that's like 5.5, 6, 6.5, 7. Which of that is that closest to? It's closest to 6.5. So 6.5, what time does that correspond with in the context of the problem? 6:30 p.m. Okay, so at 6:30 p.m., what does it mean? It means the rate at which people are coming in is the same as the rate at which people are coming out. The number of people in the festival at that time is not changing because you have the same coming in and the same going out. You have the latecomers, they're arriving, and you have the early leavers because they crashed too early, they're leaving. All right, so that's F, and then we have G. Okay, given, so we don't even have to calculate. Given the integral from 0 to 12 of dE on dt, take dL on dt, equals 296. What does 296 mean? Okay. State the meaning of the value 296 in the context of the number of patrons. Okay. I'm going to break this into 2 parts, and then it's going to be really easy for you to answer. The integral from 0 to 12 of dE on dt, what does that tell you? Yeah, exactly. It tells you how many people came in for the 12 hours. And we did it over here. This was how many people came in between 1 and 4. So between 0 and 12 of dE on dt, that tells you how many people entered the venue over the 12 hours of the music festival. Total number of people coming in. Okay, then from that we're going to subtract dL on dt. What does this tell you from 0 to 12? This is the rate at which people leave. So the integral of the rate at which people leave tells you how many people left. So we have this many people came in, this many people left. All right, so if we go, here's all the people that came in, take away all the people that left, we've got 296 patrons remaining in the venue after midnight. Okay, then maybe they're passed out or something, they've had a bit too much. They've had a good time and they're very tired. So 296 patrons remain in the venue after midnight. All right, so this is a really good example, this question, and you see this pop up in a number of the practice tests, a really good example of an applications of integration question that is drawing on lots of different stuff. Now, most of the time, you will use your calculator. Really, the only time you're required to integrate manually, to use the fundamental theorem of calculus, is if it tells you to. All right, for the problem solving, a lot of it is going to be just mash it in your calculator. Okay? So really, all you have to, you only do the do it manually if it tells you to. And you can see up here we've basically used our calculator for everything. A lot of it's interpretation, okay, graphing, just G-solving. All right, so our calculator is our friend. We won't go through exam question 2 now, Now the textbook questions for this exercise as well, we're not going to do all of them either. I mean, I recommend doing all of them, but I'm just going to select a few that I think you definitely have to do. Start with those and then you can have a look at some of the others. Okay, so I'll put a list up here on the board. All right.